at a point. It fails at all points. So these are two extremes, right? You could imagine a form which had one form where alpha wedge d alpha was 0 some places and non-zero other places, right? You can imagine a one form which is such that alpha wedge d alpha is non-zero everywhere. That's a contact form. So a contact form is pretty much as far away from this as you can get. So if a plane field has this structure, it's said to be integrable. So if this is the case, this is said to be an integrable plane field. All right, or completely integral, he says. And then the question of whether or not a given field is integrable is a difficult and technical question. But there's an elegant and beautiful answer given to us by something called Frobenius' theorem. And Frobenius' theorem, while very difficult to prove, is pretty simple to state and not that hard to remember. And yes, King, the same Frobenius as in your homework from the other course. At least I think there's only one Frobenius, and there must be, I wonder how many different Frobeniuses there are in math. It's a good question. I don't really know. As far as I know, there's just the one. What's that? As far as I know. So here's Frobenius' theorem. It states the following. Let E be k-dimensional distribution in Rn. What's that mean? With property that for all p in Rn and xp, yp in EP, all right, we have the Lie brackets of xp and yp are in EP. Then E is integrable in the sense that. So what do I mean by E is k-dimensional distribution, guys? Right, it's a k-dimensional set of vector fields. And so, I mean, he has more technical jargon in the book, and I'll let you read that. I want to cut through that noise and write it more sort of abstractly. E is integrable in the sense that E at a point P is the tangent space to S, where S is k-dimensional submanifold of Rn. In other words, if the brackets of the vector fields in the distribution close on a basis, it means that that distribution appears as the tangent space to a particular submanifold, so-called integral submanifold. You think of integrating the distribution to get the manifold, because the tangent to the manifold is the distribution. Now, he gives this in terms of a parameterization and also a level set. He doesn't write what I wrote. He writes something about a parameterization from a subset of Rn, a subset of Rk into Rn. He gives a parametric description of the geometric set, and then he also gives it as a description of the intersection with a level set of n minus k conditions, which also would describe a k-dimension. He gives both the level set and the parameterization version of the geometric set for the theorem. Don't be distracted from the rest of it. All he's saying is that this distribution appears as the tangent space to a submanifold of the same size. And vice versa. And vice versa. If, conversely, if E is integrable, guess what? Then xp, yp is an EP. Now let's see here. Does it seem like I said nothing? Depends on my language. So again, integral means that E appears as the tangent to a submanifold. All right? This condition up here, this right here, is usually said to be the involutive condition. Involutive means that the bracket of the vector fields closes back in on itself again. What's going to happen if we calculate the brackets of the vector fields of those guys? Let's try it. Ah! Yowzers. If I understand correctly, what should happen if we calculate the bracket of this one over here? There's only one bracket to calculate, right? So we got partial x plus m partial y with partial f. So we should let that act on a function f to make sure we keep ourselves honest. So we've got partial x plus m partial y partial mf minus partial m partial xf plus m partial yf. This is the kind of calculation which might appear on your test, right? We've had a bunch of these, I think. Haven't we? We have done things with brackets of vector fields. I think that's like, to me, this is a much more friendly question than, say, calculate the Christoffel symbols of the Poincare metric or something, right? I will try to be kind on the test and not make it too lengthy. Make sure you know the flux form and work form stuff, all right? And how to relate the exterior derivative in R3. Those make good questions for the test. Okay, so getting back to here, this would be partial x, partial x, partial x, partial mf, right? And then plus m partial y partial mf. And then over here, there's a product rule. You see that? But first we get minus partial m partial xf, and then minus partial yf minus m partial m partial y f. Now, most of this stuff should cancel, right? It's like this and that are gone. This and that are gone. But we're left with minus partial yf. Therefore, partial x plus m partial y, comma partial m, is minus partial y. That is not an accident. These vector fields are not involutive, right? Because this distribution is not integrable. This distribution would not appear as the kernel of the differential of a level function. And yet it's geometrically interesting, right? Now, there is a reformulation of this, theorem 6.3.8, and you have E, a plane field, given as E is the kernel of a one-form alpha, right? Right? Then E is integrable, again, meaning it appears as the tangent space to a submanifold of appropriate dimension. Then E is integrable if and only if, I said appropriate dimension, but that was dumb, right? Alpha wedge d alpha is equal to 0. I said it, but we're talking about, I think this theorem. Excuse me. Sneezed in the mic. Sorry. I'm a bad person. Let's see here. This is R3. Okay, in R3. So we literally mean plane field. It's a two-dimensional assignment of two-dimensional spaces. So I think I've given us some things to think about. You see what we're getting at, really, this whole discussion, one of its merits is it has the potential for us to understanding more deeply exactly what differential forms are and what they can be used for, right? And also, it gives us some sense of the utility of the wedge product for just checking linear. I mean, what is this alpha wedge d alpha? It just says what? Non-zero means that alpha and d alpha are linearly independent. That's what that means, right? And I sometimes wonder, you guys, what if we taught linear algebra with wedge products throughout? What if we used wedge product as our tool for understanding linear independence from the outset? What would that look like? You know, I wonder about that sometimes. That was more or less the idea of Grassmann. But these geometric algebra people, they go a step further. They think of wedge products as lines and planes and volumes and so forth, literally. It's not productive for me. I like my functions and sets and sometimes not so geometric things. I like to be able to divorce myself from geometry when it suits me. You know, always having to do geometry all the time sometimes can be a bit much. Now, the larger question is, one question obviously is what would the thing I just wrote down look like in the case that we were not in R3, how would you, let's just think about, we can think about this in the time that remains. Imagine yourself in R4, right? And you want to describe a two-dimensional distribution in R4. How would that work? How would you pick out a two-dimensional distribution of R4? Suppose I'm working in space-time. Time-space, rather. T, X, Y, Z, right? Suppose I want to look at a plane field where Y and Z are free to range. These are free, but T and X are fixed. So I want to look at my planes as being things like, E sub T naught, X naught, so to speak, If I wanted to build that as a kernel, what would that be the kernel of? Well, this one's flat, so the tangent space is there's this thing we're doing between submanifolds and their tangent spaces that I'm ignoring at the moment, sorry. I mean, this is it's a leaf in the foliation. I shouldn't say that. E, I'm thinking as the span of partial y and partial z, basically here. That's what I'm trying to get at. I don't think I've gotten at it, but that's the distribution I'm thinking about, right? So if I want to write that as I can't write it as the kernel of a one form, right? Maybe the kernel of a two form? Would this be the kernel of dt wedge dx? I mean, is that what it is? Is that how we do it? That's the derivative of what? Well, I haven't proved that that's not integrable. A derivative of t, we say that's derivative of t, tx.
Right. So if we differentiate it again, if we take the derivative again.
Oh, I agree that this is closed.
Right.
Another thing you should know for the test Friday, what's a closed form? What's an exact form? I think this one would be integrable. It's not a contact distribution. It's integrable. But I don't know. I'm not sure that that's right or not. I haven't thought about this in a while. But you see there's going to be some, like how does this idea, when we get past 3 dimensions, go to 4, 5, 6, what's this interplay between the distribution and the corresponding annihilating forms? This alpha is the annihilating form for the distribution. Anyway, I personally find this part of this course very interesting, and I have still not exhausted the questions I have for it anywhere close to done. But anyway, I'll stop here for today. Thanks, Audrey.